Well, believe it or not, we've learned all of our derivative rules that we need to learn for AP Calculus, and we just have one more area of derivative applications that we need to learn about, and that is particle motion. Particle motion is the most practical application of calculus, and we believe that Sir Isaac Newton discovered calculus while he was solving physics problems. So I like to call this little half unit our unit on physics. I call it a half unit because we'll come back and revisit particle motion after we learn the second half of calculus, which is integrals. But for now, our learning target as we start particle motion is to use the derivative to find rates of change, including velocity, acceleration, and speed. So if you've taken a physics class, you'll be familiar with these terms, and you'll learn how to connect them to the calculus that we've learned. And if you haven't taken physics before, it'll be a nice introduction to these rates of change. These set of motion functions that we'll be working with are found by taking the derivative or differentiating the position function x of t of a particle or an object that's in motion. So x of t is what represents our position, and we consider that to be our original function. A position is measured in some kind of distance units, so it could be feet, meters, miles, yards, any kind of distance, but there's no time involved in the position units. When we take the first derivative of our original position function, we end up with what we call the velocity function, v of t, and we know that when we take a derivative, we're actually making it a rate of change or dividing by time. So the units for velocity are some distance units divided by some times units. So meters per second is a pretty common unit for velocity. If we take one more derivative, so the second derivative of position or the first derivative of velocity, we end up with our motion function called acceleration, and we'll use a of t to represent that. And since we had distance per time for velocity and we took one more derivative, that means we divided by time again. So our units for acceleration become distance divided by time squared. Let's work through this example given to us to learn about the relationship between these three functions. We are given the position function x of t is equal to t cubed, and we're asked to find the position, velocity, and acceleration all at time equals 4. So taking that given function for position, I just need to substitute 4 in for my t time. I get 4 cubed, which is 64, and I wasn't given units in the problem, but let's just suppose that they're going to be meters for the distance unit of position. We just learned that to find the velocity, I need to take the first derivative of position. So using the power rule, I would get 3t squared. Velocity at 4, substitute the 4, I get 48. We're taking our distance unit meters and dividing it by time. And again, we're just supposing that time unit will be seconds to use a common unit for velocity. I think what I'd like to do is save the examples to work out in class together, so let's just get through the conceptual information about velocity in this next section. Velocity is really helpful because it gives us the numeric value and its magnitude, so how fast the object is moving, but the sign of the velocity gives us more important information, which is the direction that the object is moving. So there's three possibilities for our value of velocity as far as the sign. If velocity is greater than 0 or positive, the particle is moving right or up depending on the situation or the context. If velocity is negative, the particle must be doing the opposite, which is moving left or down. And if velocity is equal to 0, the particle is stopped or at rest. Now we'll be looking specifically at these velocity equals 0 when we're asked about changes in direction. And the particle will change direction if and only if the sign of velocity changes. So we'll be setting up some little charts that are similar to sign charts to see if that sign change has happened for a change in direction. Since we have two examples in this section, I think we'll do one in the video and save one for class. So let's go ahead and read our information. This is a released AP question. There's a particle moving along the x-axis, so horizontally to the left and right. And you'll see that's actually why we use x of t per position, because a lot of these questions are going to be a particle moving horizontally. We are given its position function, x of t. We're asked for what values of t is the particle at rest. We just discussed that at rest, or stopped, means that the velocity is equal to 0, so that's what we'll be looking at. The first thing we need to determine is, do I need to use the function I'm given, or do I need to take a derivative? And so what I like to do is set up what I call PVA ladder, my position, velocity, acceleration, and we jump down that ladder by taking the derivative. So I know I'm given my position function, so that's my starting point, so I put a point there. And I'm asked about my velocity function, so I'll have to make one jump or take one derivative to get that velocity function. So go ahead and take the derivative of my polynomial. It's just a power rule situation. And I had already decided to set my velocity equal to 0. So while I'm doing that, I notice I had a GCF of 3. I finished factoring into two binomials. I set each factor equal to 0. I know that 0 equal to 3 factor does not give me a solution. And when I look at the third factor, t plus 1, when I get t equals -1, I know that time can't be a negative number in this universe. And if I had forgotten, they do tell me that time has to be greater than 0. So my only answer that's valid is time equals 3. The last concept I'd like to talk about is speed, and that is very similar to velocity. A lot of times students get confused between the two, and they are related, but speed is just the magnitude of velocity. So it does not show direction, so it doesn't say which way the particle is moving, only how fast. So mathematically, speed is actually the absolute value of velocity. It takes away the sign. So it gives us a little less information, but it's something that we'll be asked about, particularly if an object is speeding up or slowing down. So let's look at those possibilities in this chart below. To increase speed, your velocity and acceleration need to be working together. So you need to be moving and accelerating in the same direction for that to happen, for the speed to increase. Mathematically, we need them to have the same sign, so either both positive or both negative. Oppositely, with decreased speed, we need velocity and acceleration to work against each other in opposite directions. So we'll have one positive and one negative sign for velocity and acceleration. So this chart below just explores all the combinations of positive and negative signs for both velocity and acceleration. You'll notice in the first two rows, the signs are the same, so the speed would be increasing. So instead of having to write that twice, I just made the conclusion B of t and A of t have the same sign. And in the last two rows, speed would be decreasing because they have opposite signs.